Okay, this example we're going to work as a navigation example where an airplane is traveling in the direction of 200 degrees with an airspeed of 250 miles per hour. There's a 35 mile per hour wind with a direction of 285 degrees, and we're going to answer two questions. We're going to find the plane's ground speed. I'm going to call that question 1, and we're going to find the plane's course. We're going to call that question 2. So for question 1, to find the plane's ground speed, the first thing that we're going to do is draw a diagram to help us out. So if the airplane is traveling in the direction of 200 degrees with an airspeed of 250 miles per hour, I'm going to think about starting at north and rotating around 200 degrees clockwise. So this is 180, and I'd need to go a little bit more in order to do the full 200 degrees. So I'm going to draw my vector, and it's going to be 250 miles per hour long. The next thing that I'm going to do is I'm going to think about this little small coordinate plane at the end of the vector, or at the head of the vector, and I'm going to graph the wind speed. So the wind speed is 35 miles per hour with the direction of 285 degrees. So I'm thinking about starting at north on this little miniature coordinate plane. And if we go all the way around 3 quadrants clockwise, not counterclockwise, clockwise, we hit 270. So I know I need to go a little bit more to get to 280. So my vector for wind is going to look something like this. And it's only 35 miles per hour long, so this is actually a bit longer than it would need to be. But it's going to give us the general direction here. And then if I want to find the ground speed, we're going to complete this triangle here. And we need to find the magnitude of the red vector that we drew. That's going to represent ground speed. And we also eventually are going to find course. Course would be the degree measure from starting from north and rotating all the way around to the red vector. So if we tackle ground speed first, ground speed can be found by adding airspeed plus wind speed. And so we're going to work with airspeed and wind speed in polar form. So our polar coordinates, the way we find polar coordinates is we think about r times the cosine of theta and r times the sine of theta. And in both cases, theta comes from the angle that's formed with the vector and the x-axis, and r is the magnitude. So if I'm working with airspeed first, my magnitude is 250. And then I'm going to do a little bit of think work over here to figure out what my theta would be. So my vector's down here. If I form a reference triangle with the x-axis, I would be thinking about this triangle, and I need to find theta. So for this particular vector, the direction was 200 degrees. So that's 200 degrees from north all the way around to here. So if I want to find what theta is, we can actually rotate around, go the full 270, but then subtract out the part that I don't want. So I'm thinking about 270 minus 200 to give me 70 degrees. So I'm going to have 250 times the cosine of 70 degrees and 250 times the sine of 70 degrees. Then for wind, so if I want to find the wind polar form, the length or magnitude of the vector is 35. So I'm going to have 35 times the cosine, and then I need to think again about what the angle would be. So if I'm thinking about a little miniature coordinate plane down here, only looking at the relevant part, my vector is in this quadrant, second quadrant, and so we would rotate around a full 270, plus we need to go a little bit more to get to 285. So when I'm thinking about the reference triangle right here, the extra amount that makes up theta from 270 would be 15 degrees. So I'm going to put that into my polar form. I've got 15 degrees, and I've got 35 times the sine of 15 degrees. And then the last step for both of these would be to consider whether any of these values should be negative. So if I'm looking back at airspeed, and I'm thinking about this diagram right here, in this diagram, the x value is negative, and the y value is also negative. This whole quadrant has negative, negative. So I'm going to add negatives to both of my x and y values here. And then I'm going to think again about my wind speed and think about what would be negative here. So in this quadrant, in the second quadrant, the x value is negative, but the y value is positive. So I'm going to make sure that my x value is negative, and I'm going to keep the y value positive. So then to find the vector that represents ground speed, I'm going to add the two vectors that we have. And this is where I'm going to pick up my calculator and just type in the numbers to add up this x value plus this x value, and I'm going to get a new x value. And I'll add this y, and get a new y. And it's important in your calculator to make sure you're paying attention to which ones should be negative. We're always adding, but if I'm adding a negative, we need to be careful about that. Okay, so when I calculated the values, I got negative 119.312 and negative 225.864. So this is the polar version of the vector representation for this red vector here that's representing ground speed. It is the x and y coordinate right here of the head. So to find the magnitude now, and the magnitude is going to give us the actual ground speed, we're going to take the square root of my x value squared and add that to the y value squared, just like this. So when we do that, we get 255.441, and that's in, that's in miles per hour. So that answers the question, what is the plane's ground speed? To answer the question about course, I'm going to move down so I have a little bit more room here, make this smaller. And for the purposes of this right here, we're going to ignore this. So I actually did not mean to do that. I'm just going to mark this off here. So we know we're not paying attention to this text right here. Okay, so to find the course, part 2, we're going to be thinking about the diagram and thinking about finding the angle measure that starts from north and rotates around all the way until we hit the red vector that represents our ground speed. And so if I'm thinking about what I need to do here, I'm going to use a reference triangle formed with the x-axis, and I'm going to find theta. And the reason I'm going to find theta is because if I know what theta is, I can think about a 270-degree rotation that would go all the way to here. And then if I backtrack and subtract out theta, I'm going to have what's left over, which is the rotation that I'm looking for here. So in order to find what theta is, we're going to use the information that we found in part 1 up here, and we're going to use an inverse trig function to find out what theta is. So if you recall, the tangent ratio, tangent of theta, is always equal to y over x, and we're going to use that relationship to help us find theta. So we're going to do tangent inverse. And when I'm using these values to find the degree measure for theta, I'm going to ignore or take the absolute value of these the values, the x and y values. And the reason I'm doing that is because I want to find theta from a reference triangle, and I'm not paying attention to where it's actually located based on the vector that we have here. So I'm going to punch this into the calculator. Okay, and when I punched it into the calculator, I got 62.155 degrees. That represents, again, this theta value. And I want to do 270 and then subtract out theta. So I'm going to do 270 minus 62.155, and I get 207.845 degrees. And so that represents the course for the airplane, thus the answer to question number 2. So our two answers here, our answer to question 1 is 255.441 miles per hour, and the answer to question 2, or what is the course, is 207.845.